Turns out that that's fine in practice. We don't do anything to account for it, typically. Just ignore it.
But you can have an initialization. You could initialize to 0, then there would be a problem, right?
So yeah, you have to initialize random in a random enough.
Yeah.
Okay, so if we had multiple training examples where the eyes of say human faces and the eye was just a little bit different each place, then when we run this convolutional filter, let's say this convolutional filter was able to detect eyes, and it would activate slightly different locations for these different images. One way to make that robust is to take an OR gate, which is just the maximum of all of these. So if there is an eye anywhere in here, I return that there is an eye, basically. So this is called max pooling. So this is what I mean when I say that this network actually has both a nonlinear transform, which is rectilinear, and an OR gate simultaneously before it passes the output to the next layer. One could also do L2 pooling. So you can think of it as a softer version of max pooling. You just take the square root of the sum of squares of the outputs. Right?
Question?
Yeah.
So you applied it after you convoluted, after you maxed, and then you pooling.
So yeah, it's a little confusing because max happens twice. This max is just a nonlinear transform, right? This function. This is a nonlinear transform. This is the tau, and then this is an OR gate.
Which happens afterwards.
Yep.
So you shrink the image after this is even smaller.
Yep. Yeah.
Is the max pooling, does that constitute a new neuron, or is that like you have like?
Different people will give you different answers for that. I tend to think of it. As just part of this convolutional layer. Other people will tell you a different answer. Say this is a completely separate layer. When you design an architecture of a deep neural network, you have to specify whether or not you want to max pool after this convolutional layer. So the architecture is typically fixed beforehand. Some people will say, well, if you could add or subtract this, it should be a layer. But I don't know. It's not actually doing that much interesting computation, right? So, in fact, there's not even any. Furthermore, there's no weights here, right? It's simply the max. So there's no parameters on these edges, right? So I tend to think of it as not in its own layer. Other people give you the opposite answer.
So the idea that there's like 9 different eye detecting neurons and
There's one eye detecting neuron that is sliding across the image and giving activations.
Okay.
But because the activations, depending on how in my eigenfaces thing, right? That everyone's face was a little bit shifted or whatever, right? And so something like max pooling would be able to deal with that. Or deal with that better than not doing so. Did you have a question? Yeah?
So just to confirm, so all these 3 things together is one neuron. So this is like one part.
This is one neuron that's a convolutional neuron, which gets applied as a sliding window across the entire image, or if it's a higher level hidden layer, across all the outputs of the previous layer. So a convolution applied to an image gives you basically an image, right? Yeah. And then this can be applied to the next layer. And keep in mind that in a deep neural network, there are many such convolutions. So let's say there's like 100 convolutions, right? So then the original image, let's say, has 3 channels RGB of images, of a 3-channel array of intensities, RGB. Layer 2, hidden layer 1 outputs a 100-channel array of images, intensities, but each array is smaller, right? And then the next hidden layer takes as input all these, applies convolutions to all of them, and then outputs another hidden layer of intensities, typically even smaller images.
Okay, but all these 3 things are repeated in every layer.
I'm sorry?
All these 3 operations are repeated in every layer. So every layer has like a neuron which first slides the window, then maxes, and then does.
For convolutional neural networks, it is typically standard to do all 3 of these things, yes.
Okay.
Yeah. As the designer of your own neural network, you can choose not to put max pooling here if you don't want to. But it's typically done. Another, yeah.
Is there a disadvantage of having like more, like, it's like, if you took out max pooling, like, would that ever like help you?
I don't actually know of an instance where max pooling hurts performance, which is basically what you're saying.
I thought like, even if you have something that's pretty much useless, like the rest of the neural network would just ignore it, right? When it tries to combine it back.
Right, max pooling is more about, is another way to deal with shift invariance, right? If there's some jitter across images of where the location of where an eye is supposed to be, max pooling deals with that. I don't actually know of an instance where max pooling hurts the model. I know there are cases where max pooling doesn't really help. I don't actually know of an instance where max pooling actually hurts the model. So usually people just add it. Yeah.
Are there like projective generalizations for this, where you look also for like, as opposed to just like shifting and like, you know, like tilting things like that?
Yeah, people have done rotation invariants and stuff like that more recently. They're called spatial transformer networks. They're great at coming up with names and can be funny. So recently, if you look up, if you search for spatial transformer network, they've done things like rotation invariance and stuff like that. Illumination invariance, maybe as well. So local contrast normalization is also another way of doing illumination. So the human eye, when we look at an image, we actually often don't perceive the absolute intensities. We often do relative intensities, right? So, there was this famous, optical illusion where you think two colors are very different in color, but actually the same shade of gray, which says that the surrounding context was different, right? So, and this optical illusion fooled us in that setting, but it's useful in more and more general settings because it's the relative intensities that we use typically to judge, to process images in order to do higher level reasoning. Of course, nothing here actually says anything about local, nothing here explicitly deals with the fact that we have, that the absolute intensities would be high or low, because at the end of the day, you feed this to a linear model, right? Which doesn't tell you much about high or low. So a technique that people often use is called local contrast normalization. So basically what it is, and it's a relatively fancy name for a simple thing, is you standardize the output of the convolutional layers using the mean and the variability of its estimated parameters, right? So this is the output of the convolution, and instead of passing this to through the network, we sort of mean center and we normalize it around by the neighbors, right? So mu ij is ij indexes into a cell in this array. Mu ij is simply the mean of all the f, and f is the output, all the fi prime j prime that are close to ij, right? And then we just do this. So now everything's sort of in the same scale in its local neighborhood. And this is actually biologically inspired, because the human eye does this. This particular formula may not be what the human eye does, right, but the high-level intuition is biologically inspired. Okay, so here is a method for a simple method for neural networks. So this one has a single. This one is showing a single convolutional layer. So here's the input, and then we learn 8 convolutional layers in the 8 convolutional filters in the first layer. So it outputs these 8 images. You could think of this as different channels. So the original image, there's just one channel, but in RGB images, there are 3 channels. You do a regular linear transform, so you clamp at 0. Right? If it's negative, you clamp at 0. You do max pooling, so now that the images are this big, right? And then you pass this to the next layer. So a deep convolutional network is simply stacks of convolutional filters, right? So the input image is RGB, and then we have a 7x7 convolutional, 7x7x3 convolutional filter that looks at 7x7 patches of all RGB channels of the raw image. And then we do 3x3 max pooling. So the output of this layer is 25x25. There are 10 channels, so it's 25x25x10. So the original image was 100x100x3. Now it's 25x25x10. And then the next layer takes its input, this 25x25x10 image, quote unquote image, and then with 10 channels, and it has 20 filters, and it does 5x5 convolution over all 10 channels, downsample, max pooling, downsample, you get 6x6 images by 20, and now you do logistic regression on this, right? So from 100 by 100 image, we've reduced that to 6x6, a region that has a resolution of 6x6, so, and by 20. So each of these filters fire in 36 regions, and it says there's something that satisfies this property in this region of the image, or in this region of the image, or in this region of the image. And the logistic regression says, okay, if this particular filter of 20 fires in the left region, then it means something, right, in a linear model. So these are our features to the linear logistic regression. And the whole thing is trained via gradient descent and chain rule. Question? Is that a question?
Yeah, trained at every level using gradient descent or trained at the end?
Simultaneously every level. So these are the convolutional filters are just linear weights, right? So every convolutional filter is a linear weight, and so you can figure out how that weight contributes to the error using chain rule. But there's some loss function up here, and the loss function, you could take the gradient of that, and you can figure out how this weight contributes to that loss by chain rule, and then you do a gradient step. So you simultaneously update the parameters of the entire network using chain rule by computing the gradient by a chain rule. Is there a question over here? Yeah?
So like, are there heuristics on how people pick the meta parameters? It seems like there's a lot of things to pick, like, you know, you can pick each layer, you can pick how many neurons for each layer, like all these things. So like, how does that actually?
That's a great question. You know, I'm sure there are, and I'll refer you to my PhD students who've done a lot more of the actual work on this in terms of like getting the details right. So I am hesitant to tell you too many tricks beyond the stuff that the general ones that I will present in the lecture today.
Okay.
But I'm sure there are. In the beginning, often people just try a huge swath of architectures, right? And they check live validation, etc. So downsampling just is just a compression, right? You just downsample the output to make it smaller. And so downsampling is like averaging in some sense, but you can also do max pooling as well. So people typically do both. And the way, in the terminology of deep learning, a stride is one way is how far away the next convolution is. So this need not be applied to every like overlapping adjacent set of image patches. You could jump like 3 pixels. That's called a stride. Okay, so actually the first part of this lecture I made using this online demo that Andrei Karpathy made. It trains a deep convolutional network on your browser. Oops. That. Click the wrong button. So it's doing stochastic gradient descent. This is the image that's processing through. This is the raw image. This is layer 1. The activations of layer 1. Activations of layer 2. So on and so forth. And what you see here is the chain rule gradients induced by this image. So the error is, what is the error right now? Accuracy is, so the error is about 40%, so accuracy is about 60%. Quickly go down to about 5 to 10% error, as you use the gradient set for longer. So yeah, there's one in the browser. You can try it out yourself. I would not recommend doing this for a super large data set. I mean, this is pretty small. Validation accuracy is now at 77%. Here's some example predictions. So yeah, you can actually try what would happen if you got rid of the convolutional layers by just editing this config file. Say if I just want to do linear Because this thing generalizes linear logistic regression, just get rid of the convolutional layers, you can see what happens. Yeah.
How do you know when to stop training? Because if you look, both validation error and the training error like jump around, so you wouldn't really.
So like in all stochastic gradient descent, you check after a number of, like an epoch of gradient updates. So you check after, I don't know, 25,000 gradient updates or something. And there are different rules, but that's the basic idea. You have to, in order to make these, in order for that to be stable, you have to check after some number of updates rather than every
You don't
single.
check after every single.
No, you do not. You know, you do not. Not only is that not a good idea because it's jumpy, it's super computationally expensive. Because you have to iterate over the entire validation set or training set or both, and that's actually super expensive. Okay. So the thing that I think one of the things that really put deep convolution nets on the map is the ImageNet data set. So it ran as a competition. So one of the versions of Image, one of their other versions of ImageNet ran as a competition in 2012. 1.5 million labeled training examples collected meticulously. About 1,000 classes. So these are a subset of the classes, right? So there's a mite, there's a mushroom, there's a leopard, and I guess. Spoiler alert, deep conv nets won this competition. Okay, so the deep conv net that won this particular competition, so it's gotten much better now in the 3 or 4 years since this competition. But the version that won this competition had 7 hidden layers, 5 convolutional, 2 regular. So the regular was just the ones you saw at the very beginning of the lecture. And multi-class logistic regression at the top. So this is 1,000 class logistic regression at the top layer. Trained using stochastic gradient descent. This is what it looks like. The image is, so the images were normalized to 224 by 224, RGB. So first layer has 96 filters, has a 7 by 7 convolution, 3.3 max pooling downsample by 4. So the output of this layer is 55 by 55 by 96. Then the next layer is a 5 by 5 by 96 convolution. So these are 3-dimensional convolutions, by the way, not 2-dimensional because there's multiple channels. 5 by 5 by 96, but they're 3-dimensional convolutions, but they only slide over a 2-dimensional space because they only slide over the pixels of the image. They always convolve every channel. Max pooling, downsample, what you get left is 13 by 13 by 256. So we've already subsampled from 224 by 224 down to 13 by 13. So the outputs of this filter is at this 1/13th part of the image, does whatever property this filter selects for activate, right? And there's 256 such properties, right? And then it just keeps going, right? And so at the end of the last convolutional layer, you get a 6 by 6 by 256 output. You flatten that into a vector. And then you train a fully connected hidden layer that touches every one of these, right? And there's 4,096 of those. The output of this is connected. Every output of this is connected to every input of the next hidden layer, which is also 4,096 hidden layers. And the output of this one is 4,090 is a feature vector of length 4,096. And you learn a linear logistic regression model of multi-class of 1,000 classes. And the whole thing is trained by a gradient descent with chain flow. Over about 1 million images, a million label training examples. The numbers can get quite a bit bigger these days. Like these days, I think, like the most recent state-of-the-art convolutional neural net had over 100 hidden layers, which has its own set of computational challenges, how to do gradient descent in a reliable way, but they were really solid. So any questions on this? Yeah.
So at the beginning of this lecture, you said that one of the nice things about deep neural nets is that they can actually learn features, like which features are important. Like we always said the curves. So
Mathematically, you can just think of the output of this layer as the features that we're doing logistic regression on.
right. The point here is that by putting in the convolutional part, we sort of are looking at potential features.
So all of these, even if you don't do convolution, you're looking at potential features, right? What convolutions let you do is it lets you reduce the parameter size of your model. Because convolution, the same set of 25 model parameters, 25 by 25, 25 by 9, is applied across the entire image. But a fully connected neuron, hidden layer, would have a unique weight for every pixel.
Okay, all possible connections.
Yeah. A convolutional layer says, well, actually, there's only 25 unique weights. I'm just going to slide it across the image. So it's a way of constraining the complexity of the model.
Okay, and those 25 ways are a node and its neighbors around it, something
Yeah.
like that.
Yeah. And then it's applied across the image, slid across the image. Yeah. Yeah.
So when you say downside before X, is that just averaging full pixel?
So I think in this particular case, they literally do downsampling. They check every 4th pixel. But that's okay because it's a 7 by 7 convolution. Yeah. So I think you were next, sorry.
Yeah, so so what Gotham said about training the feature and the distribution. So we're doing both at once, right? We're looking for the features and the best logistic regression at the same time. Right?
Yep.
And another thing that I think I kind of like, so what are the weights exactly here that we're like optimizing over? How does like the weights of the convolution, because the convolutional filters are kind of fixed, right?
No, the convolutional filters are initialized with random filters.
Oh, but
So-
we're not using those Gabal filters or whatever.
Those are just handcrafted. Those are handcrafted filters.
So we're
Those,
actually looking, so 96 filters.
we train these 96 filters. They're initialized randomly,
Oh,
and then we do gradient descent to train them. So the Gabor filters are handcrafted filters. So the weights are hand set. Yeah. So you're next.
Each of these layers, like on the third convolutional layer, is there like a min or a max function there too?
Let's see here.
They say max people.
No, they actually, for this particular case, they only did max pooling here, here, and here, and I don't actually know why. I don't know why they did do max pooling here. I imagine they just tried it and it didn't work as well.
So that means that those two are equivalent, could be combined into one thing, right?
No, because there's still a rectilinear transform.
Okay, so they're still doing the transform.
There's a nonlinear transform. You're just not doing max pooling. Yeah.
So it seems like in the convolutions, you're checking for features, and let's say you have like 1,000 classes, and you're trying to find like all the images that have a mite in them. And then I guess I'm not quite understanding why you would want 2 standard layers. It seems to me not in the spirit of like classifying many images as the same object.
Okay, so there's an empirical answer, of course, is that this helps. The intuition of why this might help. So empirically, it's often a good idea. Just empirically, it's ought to have fully connected layers at the end. As for why it might help, so that depends on what you think is the output of this convolutional layer, right? If the output of this guy is if these different convolutions activate. So these hidden layers can be, you can learn stack representation too, right? These hidden layers, these fully connected hidden layers, in some ways, are as expressive as the convolution of the filters, right? Because they connect to every pixel. They have a unique weight for every pixel. Whereas these convolution filters have just a 3 by 3 by how many channels of weights, and you slide it across. So in some sense, it is learning at something. Right? You could ask a question like, you know how in decision trees, right? You ask some questions of the features, and you ask other questions based on that. So something similar is happening here, right? Yeah.
So if you like believe the hype of everything that's been talked about with deep learning, it sounds like there's nothing else. You should just do this all the time. It's like, what are the drawbacks of this? Like, why isn't this the only thing anyone uses?
This particular model took 2 weeks to train.
Right. Yeah, but now that it's been like refined, and it seems like you in your browser, like.
The browser, okay, that browser was on MNIST, which is like 10,000 training
Yeah.
examples. This is 1.5 million. There's a huge, I mean, I would not recommend that browser for anything other than a toy data set.
But I guess I'm saying, like, it seems like, you know, eventually we're just getting to the point where you can train this on whatever, and it's like, is this just the right answer, or are there drawbacks for like other like, is it something we learn the rest of the class just kind of?
Everything that we've done is supervised learning.
Okay.
Do you know how expensive it was to collect 1.5 million labeled?
Yeah.
And you know, you can't do that for every data set, right?
Okay.
Like, you know, it's just not, supervised learning is inherently has an inherent ceiling that I think we're quickly realizing. This is why, by the way, a lot of computer vision research is dedicated on how do you acquire labels as cheaply as possible, right? 1.5 million labels for, and even on Mechanical Turk, that's a huge expenditure, right? And you know, you typically want redundancy because people make mistakes when they label, right? So suddenly if you collect 5 labels per instance and you know whatever all that stuff, it becomes really, really expensive. And acquiring labels as cheaply as possible is sort of a big thing. And you can make an argument that it's as important or more important than deep learning innovations in this type of deep learning research.
Okay. So like if you have labels, this is great, but if you're unsupervised, then there's like...
If you have label, if you're doing, I mean, object detection is also, you know, one of the simplest things, right?
Yeah.
Like, can this thing watch a movie and tell me that person A has a crush on person B, but person A secretly thinks that person B is ignorant? You know, it doesn't do that. It just says, is there a person in there? Because
like,
we don't have the label for that, right? How do you even collect?
Yeah.
I mean, artificial intelligence is so much beyond whether or not there's a cat in an image, which is what this does really, really well. Okay, this does this better than anything else in the world, but that's all it does. Oh my goodness.
So do people make handcraft convolution stuff?
No, everything. Not that I'm aware of. No, in general, you specify how many convolutions you want. You specify how many layers you want. You let the model train itself. Like what are the exact convolutions?
But is it advantageous if you initialize it with the handcraft version?
Not that I'm aware of. No. Yeah.
So, you know, no one brought up this issue of expense. I don't really care about expense. What I'm interested in is, are there theorems that tell me this works, or is it just like it seems to work in practice?
There are some theorems. They're not very
good.
Well, you know, they make a lot of assumptions that you know are not realistic. Under some assumptions, yes, you can prove that this is doing the right thing.
So in particular, I'm curious, but if you were to tell me for this kind of data, I need so many layers to achieve good accuracy.
I see.
Because otherwise, I could just keep looking further and further.
Right, and in fact, people have shown that if you have over 100 layers, you do even better.
Right, sure.
So, you know.
Well, I mean, in general, if I have 1,000 layers, like let's do even better, right? It can only increase. So is there something that's telling me roughly what I should aim for?
That's a great question, and I think the answer is no.
I see.
Yeah.
So just meeny, miny, mo.
I mean, people are a little bit more sophisticated than that, but there's nothing systematic like what you're talking about. I mean, and I'll get to that in a second, right? So, is there another question? Yeah. Yeah.
So if we show, let's say, 10,000 images of a cat to this machine from all possible angles and position, and then we show, let's say, only a couple of images of a dog, and tell the machine this is a dog, and then show images of the dog from different angles and position, does it realize that those are also dogs? Or
It's possible. It depends on how many sort of lower level attributes dogs and cats share in common. So what you're talking about is some notion of transfer learning, where you take a model that's been learned for one task, and you try to repurpose it for a different task, like classifying dogs. And the answer is maybe. Actually, the answer, and you'll see why when I visualize these layers. So this is the, yeah, go ahead.
So kind of along Gautam's question, but we started the whole discussion with that there's an exponential need for neurons in the fat shallow network. And
In terms of expressiveness, yes.
Right.
Yeah.
And we're saying that the deep ones are more efficient, but is there any rigorous mathematical statement on that? On the efficiency?
If you go back to that slide that I had, there's a link to an archive paper.
Okay.
Yeah, so you can prove under, again, some assumptions. It's not a general purpose proof, but under some assumptions which are reasonable, I think, you can prove that the deep ones are more expressive, require exponential or super polynomial number of hidden nodes of a shallow network. So I think the current proof says something like a sufficiently deep network cannot be modeled by any shallow network with a deep network of sufficiently deep with n nodes cannot be expressed by any shallow network with at most n cubed nodes. So it's not a general proof, like it's not exponential general proof, but I think that's the current result. But the belief, of course, is that it's exponential, by most people in the community. Okay, so let me, I'm running a little bit short on time, so let me just show you the visualization. So this is a visualization of layer 1. So all 96 filters visualized, right? So basically, some of these are actually Gabor filters. I mean, not exactly, but very much qualitatively like Gabor filters. This is learned automatically through gradient descent of these filters. These are visualizations of 3 channels. So it's sort of superimposed 3 channels of filters onto a single image, right? And so some of these are activate for certain colors, some of these activate for all colors, and many of these are actually just edge filters, right? So it just slides across the image and it activates this. So this outputs a 96 channel image of 55 by 55, and for channel 1, that channel has a high intensity in the output if there was this type of edge in that filter as you slide that across the raw input image. Okay, this is visualizing a subset of layer 2. Layer 2 is huge. So this is visualizing a subset of layer 2. So in layer 2, so this is one filter. So here I'm visualizing 9 activations of a bunch of filters, and these are the images that activate them a lot. So what can we see? Well, we can see that these filters activate on things that are more complicated than edges because they are convolutions of the activations of the previous convolutional layer. So they're convolutions of edges, basically, right? If there are edges in certain configurations in a local region, then these filters activate, right? So you get something like there's like a patch of blue, right? Or there's like sort of like a red that has a sharp gradient to black, right? Stuff like that. Go to layer 3, which is now a convolution. So the reason why they're colored like this is because it's a rectilinear transform, so it's clamped at 0. Okay? So here it's nonlinear convolutions of stuff that is the output of this layer, right? So if this is the output of this neuron for this image, right? Then that neuron gets convolved into these convolutional layers, right? So now we get things like ladder case sort of things, checkerboard, window type patterns, stuff like that, right? So these are sort of combinations of like shapes, right? Layer 4, a little bit more complicated. Now sort of the bias of the ImageNet training set starts to kick into play because there's lots of puppies and dogs in the ImageNet training set. It might be the single most popular category, actually. So here this activates, you see this activating for these type of patterns. This activates on corners, right? This activates on things that are kind of circular. What else do we see here? This actually activates on animal faces. Right? That's layer 4. The 5th layer is even more semantically rich. In layer 5, there is a filter for Siberian Huskies. So this one activates for water. Right? So this is what you get when you learn layers of convolutions of nonlinear transforms of convolutions, nonlinear transforms of convolutions. So it turns out that you need not just use this guy as features, right? You can actually